Recording in progress.
Okay, good morning to everyone. Can you hear me?
Yes, that's good.
Yes.
Yeah. Hello, Christian.
Hello, Sergey. It's 9 o'clock here. It's in the morning. We start with the first talk. Is Kuznetsov here? Yes, Alexei Kuznetsov. From the Fiber Optic Laboratory, Institute of Automation and Electrometry in Russia. Can you start, Alexei?
Yeah. Can you hear me?
Yes, Alexei, we can hear you.
Okay. Can you see my presentation?
The presentation is okay. We can see
Thank
your
you.
presentation.
Thank you for introduction. First of all, I want to give some introduction to our field. It's a multi-mode LD pumped graded indexed fiber Raman laser, and one of possibility for LD pumped Raman fiber laser is to use graded index or green fiber with parabolic radial distribution that is shown here. And as a green fiber is highly multimode, multimode LD, radiation may be efficiently coupled into the large fiber core, and at the same time, quality of the generated beam may be improved compared to the pump radiation due to the well-known Raman beam cleanup effect defined by maximum of Raman gain in the center, and thus enhancing a low order mode generation, whereas in step index fiber, the cleanup effect is weak or even absent. So using commercially available green fiber and, for instance, commercial available high power laser diodes, such Raman fiber lasers may be generated at wavelengths less than 1 microns, where high power generation of rare earth doped fiber lasers is hardly possible. So our first attempt showed about 3 watts of Stokes generation with 940 nanometers LD pumping. Then about 20 watts with M squared more than 4 was demonstrated. And finally, more than 150 watts with M squared 4 to 8 was also demonstrated by Glick. Our last results, we achieved about more than 50 watts of Stokes, generated Stokes light with beam quality m squared less than 2. So this is a good result because initially multimode pump has m squared more than 30. So we have a great brightness enhancement. And now the question is, can we use...
Next slide, please.
I want to finish here, and now we want to understand can we use instead of FBG that we used in our last work, a relay or random FBG. So the technique of on this slide there is a scheme of FBG fabrication by a femtosecond laser pulses. With this setup, we are able to inscribe three-dimension.
Sorry, Alexey, it's only a title at the moment. No next slides. We can see.
It's strange. Is it changed something? No.
Yes, now it's changed.
Yeah.
But in full screen, it's can't change. Okay. I showed this in window mode. Okay. Here's a previous slide that obviously you didn't see. And here's this slide is a scheme of FBG fabrication by femtosecond laser pulses. And with this setup, we are able to inscribe a three-dimension arrays of scattering point or FBGs. So we can rotate fiber or move it and make modification points in cross-section of fiber. The beam shape measurement showed qualitatively what are the mechanism of brightening enhancement. On this scheme, this is a scheme of our laser that we used in last our work. LD pump is broadband with spectra about 5 nanometers and has a near rectangular shape in step index fiber pigtail, similar to step index profile. After pump combiner with graded index fiber output, the pump beam tends to parabolic, similar to graded index profile of the fiber. And the process corresponds to equipartition of modes. After 1 kilometer of graded index fiber, the beam pump remains parabolic, and that leads to fundamental mode Stokes generation near stimulated Raman scattering threshold. But the pump becomes depleted at Raman laser with a deep, you can see here, induced by pump to Stokes conversion. So we have an output of laser, some parabolic profile of the pump light with deformated its shape, and Stokes beam with excellent beam quality. The generated Stokes beam is narrow in spectrum, and its profile is nearly Gaussian, with which much less of pump dip. Note that without output coupling with BG, the Stokes beam is sufficiently broader. So the mechanism of this process is, first of all, random mode coupling makes equal partition of modes, of pump modes, and femtosecond FBG spatial spectral filtering supported by self-cleaning allows to generate a near single mode Stokes beam. You can find our results in these articles. And to study model dynamics of laser with relay and at high power, we used different pump sources, homemade, incoherent, amplified spontaneous emission source with 3 dB line width of 8 nanometers, and an ordinary high-power ytterbium doped fiber laser with line width less than 1 nanometer. The spectra are shown here. The cavity of laser is a commercial green fiber with 100 micron core diameter and length 250 meters. And here's the evolution of output power and spectrum of random Raman fiber laser as a function of pump power. In case of amplified spontaneous emission pumping, those generation threshold is something like 840 watts, and its maximum power reach 700 watts. So the slope efficiency is almost 80%. Also, the line width of signal laser broadens from 1 nanometer to 1.5 nanometer with rising of pump. When pumped by ytterbium fiber laser, the threshold is a little bit high. It's 1 kilowatt, and the maximum signal power reached also 1 kilowatt. So this is some kind of record value for generated Stokes in this kind of laser. Okay, the next slide. Here is on this slide the beam quality factor m squared of injectant pump and output signal of our laser. The m squared value is almost constant. With pump power is about 19. And in case of spontaneous emission, the m squared of the signal integrates from 2.5 to about 3.8, and then rapidly grows up to 4.6, I think. Yes. And so the maximum brightness enhancement is more than 12. And now let's see on a case with ytterbium doped fiber laser pumping. Here the brightness enhancement is much lower. It's the factor of degrades from 6 to less than 1. Yeah, so this degradation of the RCA pump beam quality at maximum output power is related to the beam profile fluctuation of the signal laser. And here we have monitored the beam profile during the time, and here's the obvious instability of the output beam. Compared with the RCA pump, the output beam of random Raman fiber laser pumped by ytterbium doped fiber laser remains stable at the highest power, and this may be related to its poor beam quality. initially. And the output power of both signal and residual pump beams at maximum total output was also recorded, and it's shown here. And we see power coupling between the signal and residual pump beams with constant total output power when pumped by amplified spontaneous emission. It's anti-phase behavior. The changing of the first stokes is negligible, while the peak corresponding to the second stokes is quite unstable. You can see this. And in case of ytterbium doped fiber laser pumping, we can see an excellent stable spectra. This result shows the pump temporal stability do have effects on dynamics of random Raman fiber laser, and pumping with bad temporal stability will lead to a higher output power, while the performance of the laser in some aspects, including beam quality and spectral viewing, is poor. So in generally, pumping with better temporal stability can be more conducive to obtaining Raman laser with good beam quality. And now, in order to make generation threshold of random Raman fiber laser lower, we inscribe artificial relay scattering points in graded index fiber with different geometrical properties. Inline, 2-dimension and 3-dimension, and you can see here. Interesting that shifted inline reflector allows to select LPHYS'23 transversal mode. And the Raman threshold for tested 1D, 3D, and 2D structure slightly varies. And at maximum pumping of this 1D structure of output power of 5 watts was reached. And that output beam quality was 2.5. The estimated integral loss are comparable of this FBG are comparable, and that are 30 to 40%, and these higher losses limits the output power of our laser. Also, we try to replace long FBG with classical with random short FBGs in 1D, 2D, and 3D arrays. And this slide shows a scheme of femtosecond fabrication of this FBG. And here is the scheme of our laser. And you can see that interference of partially reflected light from individual FBGs in the random array leads to random irregularities in the spectrum with period up to 0.5 nanometers. So the mode structure is washed out. And output characteristics of multi-mode LD pumped Raman fiber lasers significantly vary for different random FBG arrays. And the threshold pump power for all of them is around 100 watts, whereas the maximum reached output power was about 30 watts. One can see that irregularity induced by interference between the individual FBGs in the reflection spectra are reproduced in generation spectra. In all cases, the generation starts from a single peak corresponding to maximum reflection, and then 1 to 3 neighbor reflection peaks also start to generate at higher powers. And then the further power increase, they're washed out. You can see this green profile. The line width of this spectra is about 0.2 nanometers up to 20 watts, and it is lower than the line width in multi-mode Raman fiber laser with regular FBG, femtosecond inscribed in green fiber, in which the interferent effects are absent. And in conclusion, here are some conclusion. So we are taking high efficiently converter from multi-mode laser emission with bad beam quality, M234 to high quality stocks. And we obtained brightness, high brightness efficiency. We demonstrated random 3D femtosecond structures and 3D array of short femtosecond FBGs. And also we have some kind of record of generated output power, I mean stocks, and shows the mode dynamics in time. Okay, thank you.
Thank you, Alexei, for your presentation. We are a little delayed. I wonder if there is some question for Alexei. No. I understand, Alexei, you are going to give the second talk also. Is that right? I have here or here you give us the both talks simultaneously. Is that right, Sergey?
Yes.
Okay. So is Kopsov here? Or,
I have something problems with sound. I can't.
Alexei, you should close this presentation and open next one.
Okay, thank you. Can you see here?
Yes, we can see your presentation is influence of model coupling on spectral characteristics of 7-core intelligent doppler fiber laser with femtosecond scribed fiber rate.
Okay, thank you.
Alex.
First of all, I want to talk about the motivation for this work. Due to outstanding characteristics, fiber lasers have occupied a significant area in industrial application, communication, medicine, space, scientific research, and etc. And these fiber lasers are characterized by excellent beam quality, high efficiency, high generated power. And also there are some certain problems, one of which is the high nonlinearity of silica glass that leads to appearance of undesirable effects such as self-phase modulation, stimulated Raman scattering, mode instability in active fibers, and etc. Multi-core fibers, as we saw in previous presentation, may overcome this limitation and offer an opportunity to develop compact all-fiber lasers with high output power. But also multi-core fibers allows to combine some generated beams to one high quality output beam. So this well-developed techniques allows this process. And the objective is to develop and investigate of 7-core all-fiber lasers with individual core FBGs. Experimental scheme of multi-core fiber laser shown here. We used a fiber-coupled multi-mode laser diode with wavelength of generation 976 with output power up to 60 watts. And pump radiation is coupled to multi-core ytterbium doped fiber, and this laser cavity is formed by a femtosecond inscribed individual coarse high reflective FBGs. They are here, and a Fresnel reflection from a straight cliff at 4% on another side. These dichroic mirrors are used to separate pump radiation so that optical spectrum analyzer and photodiodes measures generation signal. Ytterbium doped fiber, multi-core fibers were manufactured in Diana Fiber Optic Research Center, and we had 2 samples of such fibers with different geometrical properties. The first one had distance between central core and peripheral core 28 microns, and the second fiber has 17 microns, so that we expect that the last one fiber has a cross-coupling between cores. And the lengths of these fibers were chosen so that the total gain was similar in respect to cladding to core cross-section. So it corresponds to 10 and 35 meters for first and the second fiber. Here are pictures of cleaved fibers and reflection spectrum in each core. And the black line here is a geometrical mean of pulse reflection in the second fiber with cross-coupling effect. On this slide is a scheme of FBG fabrication. I have shown it previously, and both lasers with different ytterbium fibers have a similar slope efficiency. It's about 70%, and the maximum power achieved was 32 watts at 50 watts of pump power. But near the generation threshold, their behavior is something like different. In laser with fiber without cross-coupling, the generation in each core starts independently. First, the generation begins in central core, then in one of peripheral core, then in another, and so on. At the same time, in the second fiber, generation starts into cores. On this slide, there is an output spectral characteristics of laser with the first fiber without coupling between cores. And obviously that lasing is in every core occurs on own wavelength. That is corresponds to FBG's reflection maximum in each core. So the resulting lasing spectrum, it's a black line, has a relative broad line that is about 0.2 nanometers, and it's broader than an individual lasing spectra in each core. And now let's look at the second laser with fiber cross coupling. And in this situation, all core spectra are lying near the one wavelength. And corresponding resulting spectra, it's a black line again, has a much narrower length comparing to the previous case. Interesting that the spectral broadening due to self-phase modulation is described well by an estimation for a single mode laser that has described in this article. And if we'll make some correction on the mode area and geometric mean of FBG reflectivity, it fits well. To explain the observed effects, let's treat simplified model of two coupled cores. Here, normalized equation on field amplitude and eigenmodes propagating along the fiber will be coherent superposition of core modes called supermodes. And this mode propagates along the fiber amplified, but every round trip they mix with each other on FBGs because FBGs have some phase differences, and every round trip they mixes so that new superposition of modes creates. We call them eigen modes of generation, and here is condition of reflecting from FBGs. If reflection of FBGs are closed, then we can obtain a simplified solution that exists only if the saturated gain equals to the loss, and it means that the frequency of stable generation is determined by the maximum of geometric mean reflection coefficients of the grating. So actually, this result is exactly what we've seen in experiment. The generation occurs only in geometric mean of all FBGs. And what's about 7 co-coupling? The analytical is very cumbersome for this situation, and the solution can't be obtained in general form because we should also know the reflection phases of all gratings, and we can only predict that the common properties of this situation is will be similar as for 2 co-coupling, and generation will be on the geometric mean of FBG's reflection. And in future, we plan to simulate it by taking some random phases and vary these values and to get an approximate solution for 7 co-coupling situation. And conclusion, femtosecond inscription of individual core FBG is demonstrated. We are able to inscribe in every core FBG. 7 core fiber were demonstrated in 2 different fabrics, cross coupling out, some analytical model development. Co-coupling leads to supermode formation in multiple fibers that results in generation of the same spectrum across. And co-coupling effectively narrows the laser spectrum. Okay, thank you.
Thank you, Alexei, for your presentation. If there is any question for Alexei. Alexei, I don't remember if you mentioned the fiber grating length. How many millimeters is each one?
Excuse me, can you repeat how many?
The length of each inscribed fiber grating is in millimeters. The extension of each fiber grating. Will you record the next slide? Slide 4. The next one.
This one?
Is this one?
Yeah,
FBG
2 millimeters, yeah, and but every FBG has phases.
Sorry, but there is some kind of interference. Can you repeat?
Yes.
2 millimeters. Okay. I wonder if it is possible to increase this fiber grating length, or
yes, of course. Yes, of course, we are able to inscribe the long FBGs, and we have this possibility.
Okay. There is any more question for Alexei? Okay, we thanks again Alexei for both presentations, and we shift to our third talk by this DVR laser based on composite fiber heavily doped with fermion ions by Skortov. Mikhail, can you Do you have your presentation?
Yes, thank you for the presentation. Can you hear me?
Yes.
Is the presentation?
You can start.
Okay, thank
now.
you. 1 second. Okay. More time. Thank you for the presentation. And I and colleagues from Moscow would like to present the work DBA laser based on composite fiber heavily doped with erbium ions. About a few words about motivations. Single frequency fiber lasers are widely used in a broad range of applications, such as coherent telecommunications, sensing with a high spatial resolution, high power sources, for example, for second harmonic generation. This just a few of the possible applications, because single frequency fiber lasers are already used in reflectometry, also in spectroscopy and other scientific application. Distribute feedback fiber laser are the most popular among them, among single frequency fiber laser, of course, and provide stable single frequency generation due to the spectral filtering in a laser cavity formed by fiber break grating with a phase shift inscribed in the core of active fiber. The fabrication of phase shifted PBG with length more 4 centimeters is quite a challenge task in comparison with uniform PBG inscription. Considering the precise spatial position and amplitude of the phase shift to be created the inscription process. For these reasons, elaborated phase mask with phase shift in the structure or complicated point-by-point inscription techniques are used for the inscription process via continuous ultraviolet radiation and femtosecond laser pulses, respectively. Of course, using this technique, you can create unique structure. For example, it's like a 5mm DUV laser. It's described in this work. But this is redundant for the manufacture of a single frequency laser. And aside from DFB fiber laser, it is possible to achieve single frequency generation with comparable output parameters using just a distribute break reflector laser scheme characterized by cavity with an active fiber between two PBGs. A reduction in the cavity length of DBR laser based on erbium active fiber to 2 centimeters in length was achieved in this work. With a spectral line with about 1.6 kilohertz for Lorentz profile. However, the development of a DBR fiber laser with a single frequency regime based on erbium active fiber is a difficult task owing to the low absorption cross-section of erbium ions. And of course, it's a clustering problem in the case of high concentration, which result in a pulsed regime of laser generation. To avoid these disadvantages, a special design erbium doped composite fiber was developed. The optical fiber used as an active medium for DBR laser was produced via rod and tube technique, use a phosphate glass rod in a silica tube, then drawing the preform. The process of manufacturing the fiber is described in detail in this work. Due to the high concentration of active ions, the gain coefficient was about 3.1 dB per centimeter. It's so high. At a wavelength of 1,535 nanometers. And other characteristics of this unique fiber are presented. Of course, a high phosphorus concentration in the core reduce the clustering effect, and concentration of clusters decreased to 8% in this fiber, which is significantly lower than cluster concentration in commercial active fiber, with more lower concentration of active ions. And but just one moment, due to the difference in the mode field diameter between the SMF20H and the composite fiber, the splicing loss amounting to 3 dB or 50%. Despite these high total losses, the minimum fiber length required for the continuous wave laser generation was estimated to be 1 centimeter. In our case, in the experiment, the length of active fiber was 1.8 centimeter. In the next slide, okay. And taking into account the FEBG, the length of FEBG was about 1.5 centimeters, and total cavity length of 3.3 centimeters. More about cavity on the next slide. The experimental scheme of the DBA laser is shown on the slide. The high reflective dielectric mirror used in the DBA laser was deposit via magnetron sputtering on the active fiber and phase. Total thickness about 3.2 micrometers, and reflection coefficient of the structure about more than 99% at 1.5 micrometers for this wavelengths. And FEBG with a narrow spectral bandwidth inscribed by a femtosecond laser point-by-point technique. The reflection wavelength of 1,535 nanometers, and the reflection coefficient is the same, about 99% in this region, and spectral bandwidth about 60 picometers, so very narrow. Okay, the DB fiber cavity was pumped by the single mode laser diode with a wavelength of 980 nanometers and output power about 400 milliwatts through the WDM. The laser wavelengths and output power were measured using optical spectrum analyzer. Radio frequency spectrum analyzed was used to measure the relative intensity noise, and Mach-Zahner interferometer we used to determine the spectral bandwidth, and the bit signal was measured with photodiode and oscilloscope with fast Fourier transform function, which allowed for the waveforms and radio frequency spectrum of the signal to be measured. To determine the instant line width, the technique described in this work was applied where using the sequential Hilbert and Fourier transform to waveform to obtain the power density of frequency noise, of course. About results. First figure on the slide shows the measure output power as a function of the pump power. The threshold of generation was reached at a pump of 140 milliwatts. The high value of threshold power can be explained by losses of splicing between the active fiber and single mode fiber with the FEBG. I think it's these losses. This picture, these losses. Okay, the output power was reached 2.05 milliwatts at maximum pump power of 370 milliwatts, which corresponds to a differential efficiency of 0.85 nanometers or percent. Sorry, and significantly exceeds this value for typical erbium DFB laser. The optical spectrum is presented on the slide at maximum power, and the spectral width corresponds to the Orsa instrumental function, and the signal to noise ratio is 60 dB. The RF spectrum at the maximum output power presented in the inset, and the real snow longitudinal mode depicts, thus confirming the regime of single frequency generation. This is important. The measure level about noise now. The measure level of the relative intensity noise was minus 90 dB per hertz, which is typical value for this type of laser without external active stabilization. Using the technique of bit waveform process described in this work, the frequency noise spectrum was obtained, and the value of instant laser line width was determined by the level of white noise in here, and the line width was about 100 hertz. This is instant line width. And the cell heterodyne technique was used to determine the laser line width and the delay line time interval. In our case, it's 25 kilometers, and the delay line time intervals. Of course, this figure shows the RF bit spectrum with a line width of 110 kilohertz at level of minus 20 dB, which corresponds to the laser line width of 5.5 kilohertz for the Lorentz profile. And conclusion, based on this composite fiber, DBA fiber laser has been developed with the record short cavity, active length about 1.8 centimeter, and the total length about 3.3 centimeter if we take into account the length of CBG. The obtained spectral characteristic of this DFB laser are comparable with those characteristics of typical erbium DFB fiber laser, but with a significant excess of output power. And of course, this characteristic opens the path for many applications, from telecommunication to other scientific research. Thank you for the Thank you for attention. Sorry.
Thank you, Michael, for your nice talk, your presentation. Can you talk us a little about your next step in this direction, with your perspective of this work?
Yeah, we can. Thank you for the question. Yes, for reduction of losses, we inscript fiber break ratings in active fiber, but we can we will pick a mode for inscript FBG in this active fiber.
Okay.
And we can decrease the active length if we do this.
Okay, Michael. There is any more question for Mikhail? So we shift to the next talk because you are a little late.
Thank you.
Is here Mr. Spread from the Fokharov General Physics Institute of the Russian Academy of Science. Andrei?
Yes, I'm here.
Hi, Andrei. Okay. Well, Andrei worked in the Pokhorov General Physics Institute of the Russian Academy of Science in Moscow, Russia, and he will talk about erbium fiber laser source or ultra-short pulse with fundamental repetition rate of 300 megahertz.
Thank you for introducing me. Laser sources of ultra-short pulses with a high repetition rate are widely used in various fields of science and technology. They are used in high-resolution spectroscopy, optical communication, coherent tomography, or material processing. The aim of our work was to create an erbium fiber laser source with a high repetition rate of ultra-short pulses, to study the characteristic of its radiation, and to propose options for future increasing the repetition frequency. There are several ways to obtain a high repetition rate of ultra-short pulses. Of this, the implementation of harmonic modulating mode, or the creation of source with short cavity, with a high value of the main pulse repetition rate. The first approach has several drawbacks, such as instability of generation mode and poor repeatability. When implementing the second approach, difficulties also arise. One of these is the length of the active medium. Standard active fibers have relatively low amplification. Therefore, the length in cavity reaches several meters, which does not make it possible to obtain a fundamental repetition rate of ultra-short pulses significantly higher than 100 megahertz. To solve this problem, heavily doped fiber with a phosphate core have recently begun to be used. The concentration of active ions in such fiber is an order of magnitude higher than in standard fibers. This makes it possible to significantly reduce the length of active fiber in cavity. But this fiber has several drawbacks. It's degrades in air and fairly welds with standard optical components. Therefore, in our work, we as an active medium, we used a composite fiber with a phosphate core and silicon glasses. It has the advantage of standard and phosphate fibers. It's easy to connect with standard optical components, don't degrade in air, and have a high gain coefficient. This slide shows the composition of core of this fiber, to which ytterbium was also added to increase absorption at the pump wavelength. Was at wavelength of 1,300 nanometers and 1,600 nanometers was equal to 8 decibel per meter. Loss in welding with standard components did not exceed 1 decibel. The experimental setup is shown on this figure. As an active medium, we used 12 centimeters of composite fibers. These fibers was pumped by a laser diode at a wavelength 976 nanometers through a hybrid. Hybrid in our scheme play a role of wavelength division multiplexer, isolator, and optical splitter. The coefficient of split was 15%. Passive mode locking was provided by single walled carbon nanotube synthesized in aerosol placed between two FCPC ferrules. polarization control in this scheme play a role, help us to control a generation mode. The resonator length in this case was 1.9 meters. In this configuration, at a pump power of 300 milliwatts, we managed to obtain a stable regime for generation outshot pulses with repetition rate 103 megahertz and an output power of 0.48 milliwatts. In this case, the spectrum width was 1 nanometers, and the duration of autocorrelation function do not exceed 8 picoseconds. I would also like to note that there is a high signal-to-noise ratio of more than 6 decibel. Further, the polarization controller was removed from the circuit, and we gradually reduce the length of passive part of cavity. In this case, stable generation modes were obtained with outshot pulse repetition frequency 129, 153, 240, and 247 megahertz. After the maximum shortening, the cavity was only 67 centimeters. In this case, a stable regime with a pulse repetition rate of 298 megahertz was obtained at a pump power of 365 milliwatts. The laser generated pulses with a duration of 2.5 picoseconds with duration of the correlation function 3.8 picoseconds. The spectral light output radiation were 1.3 nanometers, and output power was 1.64 milliwatts, respectively. At this slide, we can see a ray spectrum, a oscillogram, and we can see that this regime was very stability, and we can see a self-starting mode regime. In the future, we plan to carry out measurement by changing the length of the active medium and reducing the length of passive fiber by optimizing splicing. Also, we plan to replace our hybrid, and at the same time, it is planned to increase the pulse repetition rate up to 500 megahertz. At this slide, you can see a conclusion. As a result, we created erbium fiber sources with high repetition rate of ultrashort pulses, and we proposed a method for increasing this repetition rate. Thank you for your attention.
Thanks for your presentation. Very nice talk. There is some time for some questions. Slide number 6. Can you shift to slide number 6?
This slide?
Here. This component, the hybrid component, this is the first time I see one of these. It's a commercial component, because here it says is a fiber element that combines the properties of a multiplexer, an insulator, and another speaker. It's a commercial component.
Yes, this element is very short for length.
Okay, and what you have here is carbon nanotube as a model locker element. Is that right?
Can you repeat the questions?
You, as a model locker, you have carbon nanotubes.
Yes, of course. We
Yes.
use single-walled carbon nanotubes.
There is some kind of degradation. There is the possibility of some kind of degradation because I understand that carbon nanotubes sometimes are broken by, for example, by Q-switched modular pools or something like that, that you need to replace this element, or is robust enough?
During of our experiments, we don't observe these effects, but this is possible.
Okay, and can you shift the next slide? Number 7 here. There is here we have the autocorrelation trace. This corresponds to a non-chirped pulse, is transform limited pulse.
We think what is pulse was chirped, but you can't estimate this chirp.
Okay, but you have not measured the degree of chirp.
Yes.
Phase. The phase of this pulse, because this is not something like a soliton emission.
Yes, and multiply wavelength on the time of pulse do not equal 1.54.
Okay.
Yes, it means that it is not soliton regimes.
And in the next slide, slide number 8, not here, the next one, number 9. Here, in the frequency measurement, here in the radio frequency measurement, there is some instability, right? That some amplitude modulation in the output train.
Yes, it was.
Yes, because we can see here in figure 8 that the pulse have different phase. Okay, and this is there is a correlation in this with the absence of the polarization controller.
Can you repeat, please?
Because in this setup you don't have a polarization controller.
Yes, this is we.
Because in slide number 8,
yes.
You don't have a polarization controller, and this.
We replaced some components in cavity on the table, and as a result, we can little bit to change the regime of working of our lasers.
Well, thank you again for your presentation. Thanks. There is some.
Thank you for your comments.
Okay. So if there is no more question, we shift to our next talk of Mr. Morozov here.
Hello. Yes.
Timur. Hi, Timur. You are going to give us your next
Yes,
talk?
on behalf of Professor Morozov, who could not attend this meeting, unfortunately.
Okay.
Yes, I would like to present this report. Just a second. Okay, can you see this presentation?
Okay, Timur worked in the Department of Radiophotonics and Microwave Technologies in Kazakh, Russia, and he will talk us about the ontology of radioactive structures as a new type of sensor. Thank you. You can start.
Thank you for the opportunity to participate. I would like to present a concept of our sensors that we have developed in our research group. As you know, fiber Bragg gratings have acquired widespread applications since their introduction in the late 1970s. They have a lot of attractive properties, such as small footprint, low weight, immunity to electromagnetic disturbances, high sensitivity, and possibility of multiplexing several FBGs into a single fiber within the single system. Unfortunately, there are some drawbacks of usage the fiber Bragg gratings. In general, here we can see on the left the typical interrogation system for fiber Bragg gratings, which is based on spectrometer, based on the CCD detector. Such systems are limited are usually limited in resolution, or they are quite costly. The principle of operation of the fiber Bragg gratings lies in the fact that the reflected wavelength, which is reflected from the FBG, shifts when the strain or temperature is applied to the gratings. The multiplexing of FBGs usually is performed using different wavelengths of the reflection, and this also can be a problem when it is necessary to use a lot of sensors, or when the spectra can overlap on each other. In order to mitigate this issue, spectrum-coded FBG interrogation methods were proposed, but we have developed another approach, which is called addressed fiber Bragg structures. This is a type of FBG which includes two or more ultra-narrow band spectral components within its spectrum response. The frequency spacing between the two spectral components lies within the radio frequency range. It is usually dozens of gigahertz. The frequency spacing between these components must be unique for each AFBS within the system, and it is called the address frequency of the AFBS. So several sensors are distinguished using this parameter, the address frequency. And it must be noted that the address frequency does not change when the sensor is subjected to a strain or temperature. Then let's switch to the classification of addressed fiber Bragg structures. In general, there are two main categories of the addressed structures. The first one is called N-pi FBG type, which are designed by introduction the two or more phase shifts in the structure of conventional FBG. And the second type is the reflecting type FBG, called N-lambda FBG. They are designed by introduction two or more FBGs with different grating periods inscribed one after another. As you can see, we can introduce 2 spectral components or 3 spectral components, or even more if it is necessary. So the structure can have symmetrical spectrum response as shown in figures A and B, and it can be also asymmetrical as shown in figures C. The asymmetrical spectral response gives us the opportunity to use even more address frequencies, since the address frequency between the first and the second component is different from the spacing between the second and the third component. The interrogation principle of the addressed fiber-Bragg structures is the following. The scheme for transmitting FBGs is presented on the left, and the reflecting AFBS is presented on the right. The scheme operates as follows. The optical source generates a wideband optical radiation, which passes through n addressed structures, 2.1 and 2.n, after which at the output of each FBS, the radiation with 2 components is formed, and the combined spectral response is approximately this one. The combined multi-frequency radiation from all of the FBS sensors is divided by means of optical splitter into 2 measurement channels and 1 in which measurement channel an optical filter with linear inclined frequency response is installed. After this filter, the amplitudes of the spectral components change according to its frequency response. And after that, they are received by the photodetectors, at which the beating signal between these spectral components is formed, which is then converted with the ADC, and analog to digital converter. We also have the third channel, which is the reference channel, which does not have the filter with linear inclined frequency response. And this channel is used to eliminate the influence of the optical source fluctuations, which can occur on the optical source. So we basically divide the output of the measurement channel to the output of the reference channel. The 2 filters with linear inclined frequency responses are used to eliminate the temperature effect on the filters. So they have different temperature sensitivities, and therefore we can take into account their temperature drifts. So here the principle of operation is illustrated. So when we have for example, the first addressed structure is stretched, and its frequency response is shifted towards higher frequencies, for example, or lower frequencies. And at the output of the photodetector, we can see that the amplitude of the beating signal increases. Therefore, we can define the basically the strain or temperature, which causes the shift of the spectrum. Consider the output optical radiation of the ith AFBS, which is represented by the sum of 2 harmonic oscillations. A and B are the amplitudes. So at the output of the photodetector, we obtain first summand is the constant value of signal. The second summand is the beating signal between the addressed components of the fiber break structure. Omega capital is the address frequency. And we also have the third summand, which is basically the beating signal between other components of other break structures. Some of them lie within the working range of the photodetector, and therefore we need to use filtering at the address frequencies to filter the component at the address frequency. So we know that the linear inclined frequency response of the filter is described with equation 3. So we can calculate the amplitudes of the frequency components of the address structure, and we obtain the system of equations for calculation of the position of AFBS spectral component. And therefore, by measuring the amplitude of the beating signal, we can determine the position of the spectral components of AFBS. Here are some possible applications of addressed fiber break structures, which we considered in our works. First of all is the load sensing bearings, for example, for automotive industry. Here we are measuring the strain of the outer ring of the bearing under the load, and it is also possible to apply FPG sensors and address fiber break structures also in intelligent tires of cars. Another application is the combined sensors, which is formed with a Fabry-Perot sensor for gas concentration measurements. And here the addressed structure can be applied to temperature compensation. It is also possible to use these sensors as in catheters for medicine as well. However, there are a few challenges despite the simple interrogation system. FBS structures in general have greater length than the classical FBGs, and the reflecting FBS they also have even longer length than the transmitting FBGs with phase shifts. It is also must be noted that the temperature and strain impact on the sensor must be uniform along the FBS length in order to ensure that the address frequencies remain unchanged when the measurement takes place. The main limitations is also the maximum operating frequency of the photodetectors, and this defines the maximum number of sensors that we can interrogate within the same system. And increase of the address frequency leads to significant increase in photodetectors costs sometimes. Then let's consider some development prospects that can mitigate the above mentioned disadvantages. First of all, we can apply the Murray recording technique of FBG, which is basically recording one FBG over another with different periods. So we can obtain the lambda FBG type address grating within the same length as the classical FBG. It is also possible to to form hybrid addressed fiber break structures, which consists of 2 n lambda FBG, and inside which FBG the phase shift is introduced, and therefore we obtain 4 different spectral components basically here. And as you can see, we can use the beating signal between the reflected peaks, and we can also utilize the transparency windows in case if we use the transmitted power from the AFBS. It is also possible to establish the address frequency downshifting, which is illustrated here. So the omega 1 and omega 2 are the small address frequencies up to dozens of gigahertz, and we can also form the omega 3 address frequency, which can be even up to terahertz. Of course, we could not see the beating signal at the photodetector at such high frequency, but we can, as soon as we know that the address frequency does not change during measurements, we can take it into account, but consider on the beating signal at the frequency omega 1 and omega 2. In general, AFBS can be used in all the applications of conventional FBG-based sensors, but they offer a simplified interrogation scheme, which can provide additional benefits such as increased measurement rate and also increased resolution. The resolution of measurement is limited by the bandwidth of the frequency components of the addressed structures. And some of the shortcomings of the AFBS technique can be mitigated using the approaches that I have told you. So thank you for your attention. If you have any questions, please ask.
Thanks, Timur, for your talk. Nice talk. There is some question for Timur. Okay, we're a little delayed. Thanks again, Timur.
Thank you.
We shift to the next talk. Is Navarro Martinez?
Yes, I'm here.
Janelli.
Yes.
Janelli, thanks for coming. Janelli works in the Instituto de Investigación en Comunicación Óptica from the Universidad Autónoma de San Luis Potosí, in San Luis Potosí, Mexico. And she will talk us about the amplitude detection of flexural acoustic waves in optical fibers by using iFiber tip interferometer.
Yes, thanks for the introduction. Good afternoon. My name is Yarel Navarro. Thank you for being here today. I am delighted to present experimental results of the amplitude detection of flexural acoustical waves in optical fibers by using a fiber tip interferometer. This work was a collaboration with Erika Hernández Escobar, Rosa López Estupiar, Miguel Ángel Bello Jiménez, Valdemar Ibarres Camilla, and Manuel Sánchez Durán. This is the outline of my talk, which consists of 5 points. First, in the introduction, fiber optic-based interferometers present some advantages in comparison with some bulk setups. These are high resolution, low cost, easy alignment, simplicity schemes, and stability. These fiber optic interferometers have found multiple applications in various fields. Some of these are, for example, in biomedical sensing, since they offer a non-invasive monitoring of vital signs such as heartbeat, blood pressure, and they can even monitor breathing. Another application is the sensing area, since they are able to measure precisely some parameters such as temperature, strain, and even pressure. This can be really helpful, for example, in structural health. Another application are the interferometric fiber optic gyroscopes. These take advantage of the Sagnac effect in a fiber loop to measure the rotation rate. They are used, for example, in navigation systems such as aircraft, ships, and satellites. Another application of these devices are the study of measurement, the displacement measurement. This can be done with a really high precision. These applications can be useful in areas such as manufacturing, aerospace, and biomedical applications. Also, numerous approaches of fiber-based interferometers have been demonstrated to detect correctly the anemometer scale vibration. Regularly, the optimal conditions or the operation limits for these systems are not discussed in the reported publication. In this work, we present a fiber tip interferometer sensor based on a standard optical fiber to characterize the amplitude of a flexural acoustic wave traveling along an optical fiber. For the acoustoptic devices, they have a lot of application in different fields, such as they can be used as an acoustoptic mode converters. These are commonly used to generate structure beams, such as vortex beams. They can also be dynamically modulated in order to allow tunable filtering of specific wavelengths, for example, or they can even use as an active modulator in a laser scheme in order to modulate to control the laser output. This is our experimental setup. It consists on a 2x2 coupler with a 50-50 coupling radio. Here comes the pump light, which enters by the port 1. This splits into port 3 and port 4. Port 3 is clipped in order to prevent any reflections into our system. And the light that travels through port 4, this is called our sensing arm. The light travels all the way here. At the fiber tip, there's a portion of the light that is returned back due to the fiber air interface. The rest of the light comes out of the fiber and is reflected by the tested fiber optic. Part of it returns to the port 4, and we can see the interference in our port 2. Here we monitor our interference output by placing a photodetector and using an oscilloscope and an spectrum analyzer in order to get a temporal and a frequency analysis. Here, the other part of the setup, we generate an acoustic flexural wave with a radio frequency source that drives a piezoelectric disc that is attached to an aluminum horn that concentrates these vibrations into a section of an encoded optical fiber. This is called the interaction region. Okay, when these beams that propagate along that returns to our setup interfere, this interference will depend on the phase difference between both beams. If we change the distance between the fiber tip and the fiber under analysis, we're going to have a signal that oscillates along maximum and minimum values. Under temporal analysis, we read our interference response as a voltage variation. The maximum and minimum signal can be expressed as a displaced cosine signal, as we shown here. We will refer to this amplitude as Pmax. When we place our fiber tip so that our output signal is located at the middle of these oscillations, we call it quadrature condition. This happens when the phase difference between both beams is an odd multiple of p-halves. If under this quadrature condition, we propagate an acoustic wave through our fiber that we are testing, the output signal will experience a displacement proportional to the acoustic wave amplitude. Here is the displacement of the fiber, and here will be like proportional displacement in our signal, in a response signal. In this case, we work under the linear approach of the maximum and minimum fluctuation. This is this region about here. This will result in a new signal modulated by the acoustic wave. We call this signal amplitude V signal. This is proportional to the acoustic wave amplitude. We can relate both amplitudes, the Vmax signal and the Vmax and the V signal in this way. So we can measure the acoustic wave amplitude. Under this analysis, the maximum amplitude we can detect is related to the small angle condition. This is the linear approach I mentioned before. Under this condition, under the conditions of our experiment, we have found this value to be 30.11 nanometers. On the other hand, the minimum amplitude we can detect is related to the noise signal of our oscilloscope. We work on an average waveform of 4, and therefore a value of 6.05 nanometers amplitude was given. Therefore, we can increase the number of average to 128 samples, and there can be obtained a smaller amplitude of 0.32 nanometers. Now, to perform a frequency analysis, we read our interference response as a frequency spectrum. Here, we consider the distance between the fiber tip and the reflecting surface as the displacement amplitude caused by a flexural wave which oscillates at an angular frequency. This frequency is the frequency that we are applying to our radio frequency source. This is to the piezoelectric disc. This frequency, by substituting this into the interference equation and considering some Bessel relations, we can obtain an expression that associates the amplitude of the first and the second harmonic of the wave amplitude with the amplitude of the acoustic wave. Here we have the first harmonic, which corresponds to the frequency we are applying to the piezoelectric disc, and here is our second harmonic. These amplitudes these harmonics are given in decibels, so we can have a relation like this. These have to be numerically solved, so we can obtain this value right here. That is the one of our interest. In this case, the maximum acoustic wave amplitude that we can be measured is 193.75 nanometers. This is considering that the first harmonic must be greater than the second harmonic. In other case, the minimum displacement that we can read under this analysis is related to the minimum, to the point where we can still be, we can measure the second harmonic, because this is getting smaller, as long as the amplitude of the acoustic wave is reducing itself. So in this case, the minimum value was of 10 nanometers. Okay, in order to analyze the amplitude, we considered an interaction region of 23 centimeters. Here we need to know which is the frequency that we are going to use. In this case, we analyzed a set of frequencies where the optimal frequency has a value of 2.071 megahertz. This corresponds to our resonance peak near 1,584 nanometers. Given the optimal frequency, we varied now the voltage applied to the piezoelectric disc to compare the acoustic wave amplitude measured under the temporal and the frequency analysis. As it can be observed, both measurements seem to correlate for all measured points. Additionally, an estimation of the acoustic power given by the piezoelectric disc is shown as a function of the voltage and so by the acoustic amplitude that was measured. Now to analyze how this acoustic wave is propagating along the fiber, we know that there's an amplitude decay as it propagates along the fiber. Here we are going to use in a future a tunable laser in order to analyze the transmitting effect when we propagate an acoustic wave along the fiber. We measured in an interaction region of 1 meter long. We measured the acoustic wave amplitude along intervals of 15 centimeters along the interaction region. We approximated this decay to an exponential decay function, and we obtained attenuation coefficient of 0.7736 decibels per meter. Now to analyze how does the acoustic wave propagates along the optical fiber, we change our signal to a burst signal. This is like a little package of the signal. We used, in fact, 210 cycles signal to get into the optical fiber. Here we can see that the fiber tip interferometer sensor let us see that when the package is propagating along the fiber. When we get our tunable laser in the resonant wavelength, we can see a transmittance response like this one. Here we can see that this part of the signal is when the package is entering into our optical region, into our interaction region. Here we can see that there's like some kind of loss because of the propagation of the burst of the package, and we can see when this package is coming out of the interaction region. So this tells a lot about how this is traveling. Thanks to we know the distance that this package is traveling. We can estimate a group velocity with a value of 2,784 meters per second, and we can even make an adjustment of the group decay by assigning a group attenuation coefficient. In this case, we got a value of 0.57 decibels per meter. Knowing this, we can even estimate what would the transmittance be if no losses were present. This would be the green line. Now, we make a little difference in our setup. We added a clamp. In this case, we use the welding drop in order for this package to travel along the fiber and reflect. So we can see with our fiber tip interferometer when it comes forward and back. This is the results we got. We can measure the time it takes for the acoustic wave package to travel back and forth, the fiber tip, the fiber optic, and thanks to the attenuation group coefficient that we got before, we can even estimate the reflection coefficient, which was 83.27%. So in conclusion, there was a simple and compact scheme for a fiber optical interferometer tip in order to detect flexor acoustical wave in optical fibers. There was a temporal and a frequency analysis, and we could describe the minimum and the maximum amplitude that we could measure with each one. We compared both methods and we got a good result. We got a decay attenuation coefficient of 0.736 decibels per meter. We analyzed the transmitting response when a burst signal is applied to the piezoelectric disc, and there was a velocity group of 2,784 meters per second and a group decay attenuation coefficient of 0.57 decibels per meter. When we added a welding drop, this is a reflecting, there was a velocity that was a lot alike and a reflection coefficient of 83.27% we obtained. Thank you for your time. I don't know if you have any questions.
Thank you for the nice talk. There is any question for Danny? I wonder how close is the tip to the fiber? Have you measured that?
Sorry?
Delta? How close is the tip to the fiber in your setup? Do you have an estimation of 1 millimeter or below?
No, it was certainly less than 1 millimeter. We couldn't measure it, but we used a lens to locate, to help us know when we locate our fiber tip as close as we could.
Okay, I understand. It's very difficult.
Yeah, it's difficult.
And I wonder, since you rely in power measurements, dust and so on can be a problem on the fiber.
Sorry?
If the fiber is some kind of dust or is dirty by the dust of the laboratory, I wonder the power is reflected, is reduced.
Yeah, it's a big problem because if there is some kind of dirt, the acoustic wave amplitude will attenuate in this point. And for example, this board signal, we can use it in our favor. For example, when the adjustment is like this, these fluctuations that we can see here are, for example, we can know that there is a variation in the radios or in the radio of the fiber, or there can be like some kind of external agent. And yes, it will be a problem. It is a problem.
Thank you, Darby. Very nice talk. There
Thank
is
you.
some more question for Darby.
Yes, could you please open the 11th slide, number 11? How did you ensure that the fiber tip is located at the maximum of the wave of the fiber? So here it is at the maximum, but it is also possible that the interferometer is placed at the quadrature point of the wave, and no fluctuations will be observed in that case.
When we, thanks to our setup, we have here a base that helps us position this optical fiber with a precise position. So when we see our signal, really we are seeing like a voltage level, like really a line. And we can see that there is a point that if we move closer the fiber tip to the other fiber, this voltage will be increasing. But there is a point that if we keep closing up this fiber, this voltage will be decaying. So there we know that we have a maximum, and it's the same with the minimum. As we move this distance, we're gonna have a variation between these maximum, minimum, and it doesn't matter if we come getting closer the fiber tip.
Oh, okay, okay, thank you.
Yeah, thank you.
Thanks again, Janely.
Okay.
Now we have the last talk. My talk is a short talk, a few minutes will be enough. Okay, here we have. Can you see my talk?
Yes.
Yes, okay. Well, in this opportunity, I will share my results of a fiber laser that we have been working this year. Is in thulium dotted fiber laser. This is a fiber laser working in around 2 micrometers, and our work was in a high repetition rate. Our objective was to reach 1 gigahertz. Of course, we are talking about fundamental repetition rate. I work here in Argentina, in Rosario. It's very near Buenos Aires. This is my city. I work in this institute, the Institute of Physics of Rosario. It's a multidisciplinary institute, but in physics, and I have here a small group of 4 researchers working in optics and photonics. And this work was a collaboration with the Laboratory of Fiber Optics of the University of Valencia and a spin-off of the University of Valencia, the FIDA company in Valencia, Spain, which is a spin-off of the Valencia University that works fabricating different kind of lasers, especially fiber lasers. They have some expertise in high repetition rate fiber lasers, so we collaborate with him in this work. Both are in Spain. The application of 2 micrometer laser source, there is a strong motivation to develop reliable oscillators with emission wavelengths 2 micrometers and beyond. This could be used in free space optical communication, low latency hollow core fiber interconnection, cutting welding of plastics, laser scalpel, eye-safe light detection and ranking, remote sensing, real-time spectroscopy, optical biopsy, and so on. Especially, we work here in the fabrication of a high repetition rate thulium dotted fibers. This laser in particular play a crucial role in a variety of applications, including high-speed optical sampling, frequency metrology, optical arbitrary waveform generation, and so on. This is the laser setup. If your objective is the development of a high fundamental repetition rate fiber laser, you need to necessarily to work with a very, very short cavity. The cavity is here, is what we have as oscillator. Is very important to say that this fiber laser is polarization maintained, is fully polarization maintained. That was our second objective. First, a high repetition rate in 2 micrometers, and second, to do so in a polarization maintaining setup, because it is known that these fiber lasers are very, very robust and they are insensitive to harsh environments. And we have used pumping in the resonant C-band. We have a pump source in the C-band of 800 milliwatts of maximum pump power. And the oscillator here is only is a very short piece of a polarization maintaining to the doped fiber plus a passive fiber between a semiconductor satellite solar mirror, one mirror, and in the second mirror we have a decorative filter, which is a very thin film directly deposited in the ferrule of the fiber optic. This oscillator is have a variable length, but is always around 20 centimeters or below. We divided this analysis in three different stages. First, we moved from relatively low frequencies, for example, 50 megahertz to 500 megahertz. And the second stage was the analysis of this laser around the 500 megahertz. And the third stage was the study of this laser directly working in our objective, which was 1 gigahertz. Here we have our first results. What we have observed here is a spectrum which is located around 2.05 micrometers. And when the frequency starts to increase, for example, to 464 megahertz, the spectrum shift to a more standard frequency, a more standard optical wavelength, for this kind of laser, which is around the 1950 nanometers. What we have here is a typical train at the output, and I say again that we always work with in the fundamental repetition rate condition. In our second stage, we start to decrease the cavity length, and we have here around 20 centimeters between mirrors, between the session and the decorative filter. And in this case, we have a fundamental repetition rate around 0.5 gigahertz, in particular 521 megahertz. And we have observed from this eye diagram that the laser is very stable since we have a very well-defined eye. And there is one component here in the spectrum that we associate possible with a single Kelly cycle. This is we are working in a soliton-like emission. And what we have here is the measurement of a single pulse. We have around 40 picoseconds, but this measurement is not really what we have, since we are constrained by the bandwidth of the photodetector. So since these pools, because our soliton-like emission have a very low energy, we can't measure the autocorrelation trace because this energy is not enough for that. And so we measure the temporal wide of these pools by using the propagation, or by a 210 meters long fiber whose dispersion is known because we measure the dispersion of this wavelength. And when we disperse the output of this laser by this 200 centimeters long fiber. We can measure the light pulse with our photodetector. And so we conclude that the optical pulse is around 0.5 picoseconds at the output of the oscillator. This is 500 femtoseconds of emission at 0.5 gigahertz. This is the output power stability at this fundamental repetition rate of 0.5 gigahertz. As I said before, a characteristic of polarization maintaining cavities is the high stability. We have here a 4-hour measurement in a operation where the temperature of our laboratory was not controlled. There was a 10 centigrade thermal variation, and we have only a small variation of 4% in the power of the output. Of course, it was not necessary to control the laser at all. It's a very stable. And this is our last result. We continuing shortening the cavity by shortening the cavity to only 20 centimeters. We have the operation of the laser at 1 gigahertz. It's a very stable laser. We have here the train of the output. We have not detected any presence of any Kelly cycle, but this could be a consequence of the characteristics of our cavity or our resonator. But we measure also that this dispersion technique, the temporal wave at the output of the oscillator, and we conclude that our laser is in every condition is transform limited, and the temporal wave is around 0.55 picosecond. This is 550 femtoseconds at 1 gigahertz of fundamental repetition rate. And we have here a short simulation of this phase. Well, to finish this presentation, the future perspective of this work, which is in process right now, is continuing shortening the cavity with only 10 centimeters length cavity. We hope we can reach 2 gigahertz of fundamental repetition rate, and we are working now also with the modelization of this laser at this optical wavelength by using the nonlinear Shadowing equation. Well, that's all. Thanks.
I have a question, Christian.
Yes,
what is expected limit, upper limit of the repetition rate in your scheme, the shortest cavity length?
Yes, in this case, since the thulium doped fiber that we use is a highly doped fiber because it has an absorption of around 340 dB by meter, and this is possible to short the cavity to, we believe, around 5 centimeters long, and this will will we will arrive to fundamental repetition rates above 2 gigahertz, and we hope to reach 3 gigahertz, but more than 3 gigahertz is a little difficult with this kind of setups. But I think that 2-3 gigahertz with this setup will be a very good result if we can reach that.
Okay.
Well, I don't know if there is any more question. Well, that was our last talk. I thank Sergey and all the participants of this seminar. I don't know, Sergey, if you want to talk us something, closing remarks.
I just want to ask all of us to thank you for nice chairing the session and nice talks presented, and hope we can have sometime this seminar in Argentina. Thank you.
That would be a very good idea.
Yeah.
Okay.
Thank you.
We finish here, and bye to everyone.
Thank you. Bye.
Thank you.